This is a stress strain curve. And it's my favorite. I love the stress strain curve. So I normally like to draw this on the board. It's kind of hard for you to kind of learn this without me drawing it on the board. But the stress strain curve, basically, if you were to draw a stress strain curve on the midterm, you should be able to say it's a stress strain curve, and it should have a shape somewhat like this. Everything behaves like this. Well, most things do. Most engineering materials do. All right. And what it's looking at is the amount of strain that is put in on something for the amount of stress that went into it. So here's what happens. So this is a stress strain curve. Very, very popular, very, very important. Okay. So what happens is you start putting some stress on a material. All right. So you start putting some stress on a material, and no problem, it's going to have some strain, okay? Some elongation per divided by the unit length. So it's going to have some strain, some strain, some strain, no problem. Now, if you put this much strain on it, and then you let go, take the force away, it's going to go back to its original size. So it's going to behave like an elastic material. It's still elastic until you get to A, and then it's not going to anymore. And I'm talking about engineering materials like steel, aluminum. You can stress those so that they stretch a teeny tiny bit, or they compress a teeny tiny bit, but then when the load is taken off, it goes back to its original size. And then what materials do is they start to, now you cannot, now when you take away the force, it's going to go back, it's going to it's going to go back to a different size. Now if I took away the force, it's actually going to have deformed a little bit. It doesn't go back to zero. It's deformed, and this deformation, we can calculate what it is because it's going to be parallel to the modulus of elasticity, the slope. All right. So when it's performing elastically, we say that it is in the elastic region of the stress strain curve. So this yellow one is the elastic region of the stress strain curve. It's typically where we want to design, because you don't want to go over a bridge that once the transport trucks have gone over it, once those forces happened, it deforms the bridge and it stays deformed. You want it to always go back. It's like a skyscraper. It's, of course, let's say you live in a tall condo building. Well, the top of that condo building, it moves, right? But you don't want it to move and then stay moved. So we as engineers, we design in the elastic region of the stress strain curve. This is where we need to be, or else things break. So in there, the slope is called the modulus of elasticity. Modulus of elasticity. And if I were to write down how to calculate the modulus of elasticity, it would be stress over strain, right? Rise over run. Stress has an equation, force over area. Strain has an equation, delta L over L. So if I were to rewrite that, force over area times what's in this denominator here would be L over delta L, because I need to flip it. All right, so basically the modulus of elasticity, E, is equal to force times L over A delta L. And that has the same units of stress, which is newtons per meter squared. And that is called the modulus of elasticity, or the elastic modulus. So that's an important equation. That's the modulus of elasticity. And we want to design here because we don't want things to permanently deform forever. That would be kind of a strange world. All right, so that's elastic region, and we again want to design in that region. So I'm going to say design here in the elastic region. All right, so now things get interesting. So we get past this elastic limit, which understandably and on purpose, I'm kind of glossing over a little bit. And then things start to yield, and they yield at the yield stress. So yield stress I'm going to do actually in red. All right, so yield stress is really, really bad. So yield stress. So I call that sigma y. Different textbooks call it different things, but it's very, very famous. So basically you need to know, don't stress past yield. Don't stress anything past the yield stress. So if you're designing some equipment and you're choosing a material that has a low sigma y, this is a material property. Then don't choose it unless your forces are really, really small. So if you go past yield stress, and yield stress is here, okay, or maybe it's at B. It's kind of hard to see on this plot, but all I want you to know is around here, sigma y is the limit. Then yielding occurs. What does yielding mean? Yielding means we've gone into plastic deformation. So that bridge that you just drove over with a transport truck is now plastically deformed. It's not going to go back to its original shape. Now it's undefined. I don't know how much it deformed. Well, why would I design a bridge that all of a sudden when it gets loads, it has a different shape, a different size? That's like a skyscraper turning in the wind and then staying turned. We don't design in that region. It's very, very bad. So this plastic region is past yield. It's very, very bad. Don't design in there, because then look at the bad things that happen. It plastically deforms. Oh no, it's deforming. So then when I take off the stress, look at how big this is now. This is the new size. This is the new size of that device. Well, if let's say this is gears, you don't want them to be a different shape gears once you've run the machine, right? So you've you basically are stretching the material and it'll never go back to its original shape. It's very, very bad. And then what happens over here is even worse. I'm running out of colors to describe how bad it is. This is starts to kind of get to a point of no return. And that's called the UTS, or stress UTS, because on the stress axis, this is stress UTS. Ultimate tensile stress. It means everything is just going to pieces and it's falling apart. Falls apart quickly. It is failing. And then ultimately, of course, it's going to fracture, which means now it's in two pieces. But make no mistake, you don't want to like fracture. This doesn't mean it broke here. It's breaking here. It's breaking here. You don't want to. You always need to be in this region. All right. So that's kind of fun. So what I've done is I've defined, and I'll post a video for you of some other people explaining the stress strain curve. I recommend you go over those videos just so that you have a good handle on what the stress strain curve is. I'm going to give you two more definitions here before we go. And just to recap, modulus of elasticity is E, which I wrote on the curve. It's the stiffness in terms of just stress and strain. And the ultimate tensile stress we defined as well. Here, tensile stress has reached the absolute limit. Starts to fail. And I should also define in here yield. Stress equals sigma y, and all materials have a different yield stress. You'll start to memorize the like 101 point, or sorry, like 110 megapascal yield stress, for example, for common materials. So yield stress is the stress beyond which plastic deformation will occur. So you want to design well below that yield stress. So in the elastic region, of course, we want to be in the elastic region. So the curve looks something like this. And the elastic region is where it is a nice straight curve before things start yielding. In the elastic region, then there's a slope, right? There's a stress strain relationship that has a slope, and the slope equals E. So E equals rise over run equals sigma over, so it's stress over strain. Therefore, rearrange this, you get stress equals E times strain. So the slope in the elastic region, which is where we want to design, is called that modulus of elasticity, or Young's modulus, and it's defined as force over area. So I drew what that was on the diagram, and I'm just going to summarize it here and steal you for one extra minute. But on the diagram, I said delta L is force over area times length times E, and K is equal to E A over L. So elastic region is force over delta L times L over A, which is stress over strain. So these are not new equations. What I'm doing here is summarizing everything from the whole lecture, bringing you to the same point that elastic modulus is stress over strain. So you're going to have to go offline and think about how I made these connections, or maybe it was more simple the way I wrote it here. As the same thing there. So that's your relationship between stress and strain when we look at materials and how materials are affected by the forces that we put on them.